Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 3.4, the chain rule.
Lesson 3, the derivative of a to the x, and an alternate notation for the chain rule. Okay, so now we've seen many examples of using the chain rule. Sometimes we have to involve a second rule, and sometimes we have to use the chain rule more than once, as we did in the previous two examples when we had three functions composed together. Well, let's go ahead and go to our next topic. It turns out that knowing the chain rule allows us to figure out the derivative of a type of function that we haven't talked about yet. The derivative of a to the x, an exponential function. And remember that in this exponential function, we are thinking of a as being a positive constant. So a equals a positive constant, but it can be any real number. And in an exponential function, the base is a constant, and it's up in the exponent that we have our variable. Examples of exponential functions would be things like f of x equals 2 to the x, where the base is a constant. Well, you might say, hey, wait a minute, I already know the derivative of one exponential function. We know the derivative of e to the x. That is an exponential function. Remember, e is a constant, and e is approximately equal to 2.718. So this looks roughly like the function 2.718 raised to the x, although the actual decimal expansion of e is non-terminating and non-repeating because e is an irrational number. But you might say, wait, I know the derivative of at least one exponential function, and that's true. What is the derivative of e to the x? Well, it's a rather special function. We said the derivative of e to the x is itself, e to the x. So that's a very special kind of function. But we have not talked about the derivative of other exponential functions with a different base. For example, what's the derivative of 2 to the x? We don't know. What's the derivative of 7 to the x? Again, we don't know. Well, it turns out we can use the fact that we know the derivative of e to the x together with the chain rule that we've just learned to sort of bootstrap our way into figuring out what the derivative of 2 to the x is, 7 to the x, and in fact any exponential function of the form a to the x. Well, let's see how we would do that. First of all, we have to remember that e to the x and ln of x are functions that have a special relationship to each other. So remember that e to the x and ln of x are called inverses of one another. And remember that a pair of inverse functions such as these are functions that exactly undo one another. And what do I mean by saying that those functions undo one another? It means that if I compose them, they exactly undo the effect of the previous function. So let me explain what I mean by that. If we look at e to the ln of a, notice what's happening here. I start out with some expression a. I plug it into the natural log function ln. And then I take that output, ln of a, and plug it into the e to the x function. So ln of a goes inside the e to the x function. I've really composed e with ln, and my input into this composition function is a. Well, if e to the x and ln of x undo each other, it means that when we compose them this way, we roughly say that they cancel each other's effect out, and we end up back with whatever expression we started with. So I start with a, I have ln do whatever it does to a, I get some output from that, then I plug that output into the e to the x function, and I get back to the value that I began with. Same thing if I compose e to the x and ln of x in the other order. If I start out with any expression a, I plug it into the e to the x function and get some output e to the a, and I take that output and make it my input into ln. Well, these two functions are inverses, meaning that they undo each other. Very roughly, we say that they cancel each other's effect out. And I will get back to whatever I began with, the a in this case. So these two functions undo each other, and these are usually referred to as the inverse properties of e to the x and ln x. Well, we're going to use that fact to try to rewrite a to the x as e to the something. Now, why would I want to try to rewrite a to the x as e to the something? Because we know what the derivative of e to the x is. It's e to the x. And we do not yet know what the derivative of a to the x is. So I'm going to start by rewriting a to the x in a more complicated form that involves e to the something. Now we have to think about it a little bit. Think of this a to the x that I have over here on the left-hand side of my equation as the capital A in these inverse properties up here. I want to rewrite a to the x as e to the ln of something. And what would have to go in here? Remember that these two functions roughly undo each other. So if the e and the ln were to cancel out, I would have to have an a to the x here for the left side of my equation to equal the right side. If you want to, again, you can think of this a to the x that I have here as my capital A. So we're really saying capital A equals e to the ln of capital A. In this case, a to the x equals e to the ln of a to the x. So it's just a more complicated way, I'm going to write it again here, to rewrite a to the x. But at least I've gone from a function that I don't have any idea of the derivative of to something that is an e to the something type of function. And so hopefully that will, down the line, allow me to find the derivative of that expression. Okay, I want to remind you of another property of logarithms that will help us in this. When we have ln of a to, say, the r, do you remember what you're allowed to do with the exponent in an expression like this? Remember that you are allowed to take that r and pull it out in front to be a multiplied factor in front of the ln, the log function. So it's just a property of logarithms that you learned back in pre-calculus, that you can pull this exponent out to the front, and ln of a to the r is exactly the same as r times ln of a. So this is really just a property of log functions from back in algebra or pre-calculus. I'm going to use that here because you notice on the right side, if you just think about this, what's in the exponent of the exponential function here. So I'm just looking at this little portion up here, that I have exactly this situation where I have an x in the exponent, and my property of logs allows me to pull that x out to the front. So I'm going to rewrite what I have circled in green here and say, well, that would be the same thing as e raised to the x ln of a. And all I've done is taken this power on the a and pulled it out to the front of the natural log function. I'm going to rewrite it in a slightly different form still. What we mean by this is x times ln of a, and I'm going to write it as ln of a, that number, times x instead. So I just reverse the order of these two factors up in the exponent. Now I want you to remember that a is a constant, so it's some number. Think of a as being 5 or 2 or 7 or something like that. That means that ln of a is also just some number. It's some constant. So I'm going to put in parentheses, it's a constant. So if a is a constant like 5, then ln of 5 is going to be some particular number. You could get an approximation for it by plugging 5 into your calculator and hitting the ln button. Okay, next thing I'm going to do is I'm going to say, well, the left side of my equation equals the right side of my equation. So the derivative of the left side, which is actually what we're hoping to find, we want to find a formula for the derivative of a to the x, should be equal to the derivative of the right side. as long as I take the derivative with respect to the same variable x. So if the stuff in purple, a to the x, equals the stuff in purple on the right side, e to the ln of a times x, then the derivative of the left side with respect to x should equal the derivative of the right side with respect to x. This is really what we want to find, and now we're hoping that the right side is something that we can actually find. Well, let's think about the right-hand side. It's e, and inside the e function, I have the function ln of a, that's some number, some constant, times x. So the right-hand side is actually a composition of two functions. There's an inner function. My inner function is this, ln of a times x. It's a number times x. So I could think of that as my g of x. And there's an outer function, which is really the e to the x function. So it's a composition of two functions with an inner function and an outer function. And if I want to find the derivative of a composition, well, what rule do I need to find the derivative of a composition of two functions? I need the chain rule. So I'm going to go ahead and use the chain rule to find the derivative of the right-hand side. Let's go ahead and remember what the chain rule says. I'll write out the pattern right here. It's the derivative of my outer function, evaluated at my inner function, times the derivative of my inner function. So on the right-hand side here, I'm remembering that my outer function, f of whatever, is equal to, well, the outer function is the e to the x function, so that would be e to the empty parentheses. That's the thing I'm usually thinking of in my head. So I want to go ahead and take the derivative of the outer function, but the derivative of e to the x, we said it's its own derivative, it's e to the x. So when I take the derivative of the outer, I get the same function back again. I get e to the whatever. Derivative of e to the x is e to the x, so if I replace the x with empty parentheses, that would be e to the empty parentheses. Well, what goes inside that, that's the derivative of the outer, I'm supposed to evaluate that at the inner function, at my g of x. And my g of x is exactly what I underlined in this wiggly green line here. My g of x, the thing that goes inside here, is ln of a times x. So what we've done so far in the chain rule is we've done the derivative of the outer and we've evaluated it at the inner function. The only thing I have left to do is times the derivative of the inner function. Now when you look at this inner function, it may look complicated because we've got ln of a times x. But remember that ln of a is just a constant. It's similar to if I asked you to find the derivative of any constant times x. Or if you want to think of a specific constant, such as the derivative of 10x, what's the derivative of 10x? Well, derivative of 10x is just 10. The derivative of any constant times x is just c. C times x, it would be just c. So the derivative of ln of a, that constant times x, should just be that constant. So it should be ln of a. So, sort of a remark off on the side, the derivative of this inner function is actually very simple. It's just whatever number is multiplying my x, whatever constant I have multiplying my x, and that constant is ln of a. So, we've done the derivative of the outer, e was its own derivative, evaluated at the inner function was the number ln of a times x, times the derivative of this inner function, but since it's a constant times x, the derivative of a constant times x is just that constant, and that constant is ln of a. Well, let's just go ahead and try to rewrite this one more step. I'm going to pull this natural log of a number to the front since it's a constant. It would be times the rest of this stuff times e to the ln of a times x. But you might notice that we can actually simplify that. I have e to the ln of a times x. That would be the same thing as e to the x times ln of a. And this x that's out in front could be pulled back into the exponent. I'm using this property of logarithms backwards. So I'm going to rewrite this again as the number ln of a times, and now concentrate on what's in the exponent here, circling that in green, and I'm going to take that x that's out in front and pull it back as an exponent inside the log function. So I have e raised to the ln of a to the x, and we've pulled this x back up, and now it's an exponent on the base a inside the natural log function. Well, you might think, why is she doing all that? But you may notice that something simplifies here. If I look at what expression is left here, I have I have an ln of a out in front, and then I have an e ln of a raised to the x. Remember that, so all of this is inside the natural log function. I can cancel the e and the ln of a. We say that they undo each other, so roughly they cancel each other's effect out. I'm using this property of the inverse property of exponential functions and natural log functions. So what do I end up with here? I have this factor in front, that's the number ln of a, whatever number that comes out to be, and these have undone each other, so that's times a to the x. What do I end up with then? If you start out here where we started taking the derivative of a to the x, we said it's the same as the derivative of the right-hand side, and that derivative turned out to be this. So the derivative of a to the x turns out to be ln of a, and that's just some number, times a to the x. So we're saying that's the derivative of a to the x. That's our formula for the derivative of a to the x. We'll do a few examples in a moment, but I just want to mention that the derivative of e to the x turns out to be e to the x. It's as if the constant that's out in front here is just a 1. The derivative of a to the x is almost equal to itself. It's almost equal to a to the x, but there's this extra factor of this constant, ln of a, whatever number that turns out to be, times a to the x. So it's almost its own derivative. E to the x is special in that its derivative is itself, but a to the x is almost equal to its own derivative, but we have an extra factor of ln of a in there. Well, let's do some examples so we can get used to using this brand new formula for derivatives, the derivative of an exponential function where the base is not necessarily just just e, but could be any number. All right, so I've rewritten the formula up here, the derivative of a to the x, just so we have it to refer to on this next page. Suppose I ask you to find the derivative of 2 to the x. Well, then that means that in this case, my a is just equal to whatever the base is, 2. And according to this formula, I would end up with, derivative of 2 to the x is almost equal to 2 to the x, but there's an extra factor of ln of 2, whatever number that is, times 2 to the x. So the derivative of 2 to the x, it's almost its own derivative, but there's this sort of extra fix-it factor that we need out in front. This would be the exact answer, but just to remind you that ln of 2 is just a particular number, I plugged ln of 2, I found it on my calculator, plugged in 2 and hit my ln button, and ln of 2 is approximately 0.6931. So the derivative of 2 to the x is approximately 0.6931 times 2 to the x. It's almost its own derivative, but it has this extra factor in front. Derivative of 7 to the x, what would that be equal to? Well, it's the same formula where instead of an a, I'm going to replace all my a's with my base, which is 7. So that would be ln of 7 times 7 to the x. And that's the exact answer to our problem. If you want to, you can throw 7 into your calculator and push your ln button, and ln of 7 is approximately the number 1.946. So the derivative of 7 to the x is roughly the function 1.946 times 7 to the x. Let's try this formula on e to the x. We know that the answer to the derivative of e to the x should be e to the x. So what I'm going to do is think of a as being e in my formula up here, and I'm just going to double check my formula and see if it checks out correctly for what we know the derivative of e to the x should be. So if I go over here to the right hand side, I'm going to replace all of the a's that I see with an e, and I would end up with ln of e times e to the x. Well, remember, ln of e could be thought of as ln of e to the first power, because e is the same thing as e to the first power. And if you look at this, I have an ln and an e stacked up next to each other, and by my inverse properties I could cancel these two out, or say that they undo each other. So on the side here, what I'm really saying is that ln of e is the same thing as ln of e to the first. These two things undo each other, so that's the same thing as just the number 1. So ln of e to the first power, these cancel out, and I would just get a 1 here. So I get an answer that's equal to 1 times e to the x, but of course 1 times e to the x is just e to the x. So we do get the answer that we expect to get, derivative of e to the x, its own derivatives, that's e to the x, using this more general property. So this property works for every base, including the base e. All right. So let's go ahead and look at a final example on this page that's a little bit more complicated. We want to find the derivative of 7 raised to the 3x squared minus 1. Well, if we think about this function, there's an inner and an outer function. It is a composition of two functions. So I can see right here that 3x squared minus 1 is an inner function. We could think of that as our g of x. So we have a g of x that's inside the 7 to the x function. So our outer function here is really 7 to the x. If I write it with empty parentheses, f of whatever is 7 raised to the whatever. So f of g of x would be 7 to the g of x, and g of x is what we're calling 3x squared minus 1. So again, this is sort of what I'm thinking in my head about the outer function, and my inner function is 3x squared minus 1. Well, it's a composition of two functions. There's an inner and an outer function. So if I want the derivative of a composition, what rule do I need? I need the chain rule. So we have to use the chain rule to compute the derivative here. And remember, by the chain rule, I'll go ahead and just sort of write out the pattern. We're doing the derivative of the outer, evaluated at the inner, times the derivative of the inner function. So I start with the derivative of the outer function. It's a little tricky in this case because it is an exponential function. So we actually did the derivative of 7 to the x up here. Notice we got ln of 7 times 7 to the x. So I'm just going to do that on the side here in another little cloud. If I take the derivative of 7 to the x, we set up here, that's going to end up being ln of 7 times 7 to the x. If I wrote that with empty parentheses everywhere I see an x, we'd have the derivative of our outer function is the number ln of 7 times 7 to the empty parentheses. So let me write that in red because it's hard to see with that cloud that's there. The derivative of our outer function is ln of 7 times 7 to the empty parentheses. And I'll just complete my green cloud there. So that's the derivative of my outer function. So let me kind of write that down. I've got derivative of this outer function is going to be ln of 7, that number, times 7 to whatever I'm evaluating that outer function at, or the derivative of that outer function at. So derivative of the outer function looks a little weird, but that's the derivative of my outer function, 7 to the x, and I want to evaluate that at g of x, at my inner function. Well, what is my inner function? G of x is just 3x squared minus 1. So that's the derivative of the outer evaluated at the original inner. Now don't forget, by the chain rule we still have to multiply by derivative of the inner, but that's not too hard in this case. Derivative of 3x squared minus 1 would just be 6x. So derivative of the outer evaluated at the original inner times derivative of the inner function. Okay, so let's see, we would end up with ln of 7 times the 6, usually we put the 6 in the front, times an x, and oftentimes we'll put parentheses around this so it's clear that the x is not inside the natural log function, and then all of that multiplied by 7 to the 3x squared minus 1, and you can put parentheses around this if you want, or if you're very neat and tidy and it's clear that all of that's in the exponent, you don't have to have parentheses. So I just pulled some of these factors to the front, the 6 and the x pulled to the front, times the constant ln of 7, and that whole thing multiplies 7 to the 3x squared minus 1. So that would be our answer. If you want a little bit more of a feel for the fact that ln of 7 is really just a number, we could go ahead and do an approximation of that. And I took 6 times natural log of 7 on my calculator, and this number right here turns out to be approximately 11.675. Then I still have an x here times 7 to the 3x squared minus 1. So I could write my answer that way, but it's only an approximation to the answer, since ln of 7 is something with an infinite decimal expansion. Okay, so we are done talking about the derivative of a to the x. Now we know how to find the derivative of any exponential function with any base at all, not just the derivative of e to the x. So that's great. We've greatly expanded the number of things we can find the derivative of. The last thing I want to do in this section is to talk a little bit about an alternate form of the chain rule, using that alternate notation for the derivative. You might remember f prime of x can also be written as dy dx. And the reason we want to talk about this alternate form of the chain rule is that it will give us an intuitive idea of why the chain rule is true. You might remember that at the very beginning of this section, I just stated the chain rule, and you took it on faith that it was correct. I think we checked it for one particular example, but that is not a proof. And the proof of the chain rule is quite complicated. It's in the appendix of your book. We're not going to go through proving it, but I do want to give you an intuitive feel for why the chain rule is true, and that's what we'll be doing in the next couple of pages. Okay, so let's go ahead now and look at this alternate notation for the chain rule. And to do this, I'm going to have you do a little thought example, and that will help us to understand this alternate way of writing the chain rule, and it'll also give us an idea for why the chain rule is true. Suppose that you're in some race, like a relay race, and you run 4 times as fast as Ursula runs. What I'd like you to do is to think of y as representing your distance, and think of u as representing Ursula's distance. And so if we were talking about the fact that you run 4 times as Ursula, we could express that in symbols by saying the amount that your distance changes, which I'm going to call dy, think of it as an infinitesimally little small change in your distance, compared to the change in Ursula's distance. And again, I'm going to write du as if it's a very infinitesimally small change in Ursula's distance. The rate of change of your distance with respect to hers is equal to 4, because you run 4 times as fast as Ursula does. Let's do the same thing with this second statement here. It says Ursula, in turn, runs 3 times as fast as Zeno. So again, we're going to think of u as being Ursula's distance, and let's let x equal Zeno's distance. Well, I could go ahead and write the symbol du dx, where this would represent the rate that Ursula's distance is changing with respect to Zeno's distance. And we know that that rate is 3. Ursula runs 3 times as fast as Zeno runs. Now I want you to try to answer the question, how fast do you run compared to Zeno? So you run 4 times as fast as Ursula. Ursula in turn runs 3 times as fast as Zeno. And now I'm asking, how fast do you run compared to Zeno? And hopefully your intuition will give you an answer to this. You run 4 times as fast as Ursula. She in turn runs 3 times as fast as Zeno. So you must run 4 times 3 or 12 times as fast. So I'm going to say you run 4 times 3 or 12 times as fast as Zeno. Well, let's also write that down in symbols. If I want your rate of running compared to Zeno, I would write that as the change, the rate that your distance changes compared to Zeno's distance. So I would write that as dy dx. That's the rate of change of y with respect to x. And what we just got through saying is that's 4 times 3, or a total value of 12. So right underneath this line, I'm going to write down what the 4 and the 3 were in terms of symbols from up here. So I'm going to write the following, that dy dx is equal to, and the 4, remember in symbols, was dy du, and the 3 in symbols from above was du dx. Well, what is this really saying? It's really saying that these linked rates of change just multiply together. It's exactly what our intuition says. You run 4 times as fast as Ursula. She in turn runs 3 times as fast as Zeno. You will run 12 times as fast as Zeno. And what you really did there was you multiplied 4 times 3 gave you 12. So these linked rates of change multiply together. So I hope that this statement sort of makes sense to you, that you would end up running 12 times as fast as Zeno. Okay, now what I'd like us to do is look at what I have written down here near the bottom of the page. I said, let y equal some function of u. Well, what do I mean by that? If you think about it up here, y, remember, is your distance, u is Ursula's distance, and there's clearly a relationship between those. Maybe we don't know exactly what function y is of u, but it's some function of u. Ursula runs some distance, means that you will run some distance, because we know that you run 4 times as fast as Ursula. So y is some function of u. Your distance is some function of Ursula's distance, and I'm calling that function f. Well, if I talk about dy du, that's really the derivative of this function, and I could use our alternate notation for the derivative. Instead of dy du, I could write f prime of u. The same thing could be said about Ursula and Zeno. U is Ursula's distance, x is Zeno's distance. There's clearly some relationship, some functional relationship between Ursula's distance and Zeno's distance. So we could say Ursula's distance is some function, I'm calling that g, of Zeno's distance. Then du dx is the derivative of this function. And so I could write it using our functional notation. I could write it as g prime of x. Notice also up here that if I'm saying u is equal to g of x, well, that's this thing right here. This is g of x. That means that I could describe y as f of g of x. Y equals f of u. U in turn is equal to g of x. So I could write y equals f of g of x. That's just y equals f of u. If I do that, the derivative of y with respect to x would really be the derivative of the right-hand side. So I could write it with my operator notation and say, oh, that's just the derivative of the right-hand side, f of g of x. There's one other little thing that I'm going to point out here. This f prime of u, remember that u is really just g of x. So this line could also be written as f prime, and instead of a u in here, I could just stick in a g of x. Well, why did I go through all of this? What I want us to do is go back up to this line, and I want to rewrite that whole line. Instead of using the dy dx type notation for the derivative, I want to use the f prime type of notation for the derivative. Well, let's rewrite each part underneath it. Here, we said dy dx is all of this stuff. So in place of dy dx in this line, I'm going to write this. It's the derivative with respect to x of the composite function f of g of x. So that is just the left side of this equation. Now let's look at these two factors that are on the right-hand side. dy du, well, we had that. Where was that? dy du was right here. So this first factor on the right side is the same as f prime of g of x. And then I'm going to put times, because I can see there's a times here. And the second factor on the right side is du dx. Where is that? That's right here. Du dx is g prime of x. So here I'm going to write times g prime of x. And all I've done is translate each of these things into the alternate notation for the derivative. But what do I have in this purple line that I've written down here? I have the derivative of the composite function, f of g of x, is f prime of g of x times g prime of x. Is that a familiar statement? It is. It's exactly the statement of the chain rule. So what I have written right above it is also the chain rule, but it's the chain rule in the dy dx type notation. In dy dx, I'll say type notation. It's really the alternate notation for the chain rule. So what I have written in purple is the chain rule, and what I have written in green is the chain rule. So this is what we call the alternate notation for the chain rule. Or you could think of it as the chain rule simply written in the dy dx type notation. And here is our original form for the chain rule. And remember that this alternate form kind of made intuitive sense. It was really saying that linked rates of change just multiply together. If I want to know how fast I run compared to Zeno, I do my speed compared to Ursula, 4 times as fast as Ursula, times Ursula's speed in terms of, or compared to Zeno, 3 times as fast as Zeno, and I multiply those together. So linked rates of change simply multiply, and that's all the chain rule is saying, whether it's in this alternate notation or our original notation, is that linked rates of change multiply together. So it's a way of having some idea of why the chain rule is true, at least in an intuitive sense, by thinking of these factors in the chain rule on the right-hand side as being rates of change. Okay, well, I want us to do one example where we use the chain rule in the alternate notation. Just to show you how that works, I found most students prefer to use the chain rule the way that we've discussed up to this point in this section, using the f prime type of notation instead of using the dy dx type of notation. Well, as a last example in this section, let's go ahead and do one problem where we use the chain rule in the new alternate notation. Now, I found most students prefer the derivative of f of g of x version of the chain rule rather than the dy dx version, but I wanted us to do at least one example together where we use this alternate version. So, suppose I ask you to find dy dx, and I tell you that y is equal to cosine of 4x squared minus 5. Well, I can see that I need the chain rule for this problem because there's an inner function, namely 4x squared minus 5, inside of the cosine function. So I have a composition of functions. I must use the chain rule to find the derivative. But instead of labeling this inner function as g of x the way we normally do, we're going to label it as u. So notice what that means. It means that y is equal to cosine of u. So I'm going to write y first of all with an input of u, and then u in turn is what we're setting equal to 4x squared minus 5. And the chain rule, if I were to write out the pattern for it, I'm going to put that right down here. It would say if I want dy dx, how do I find it? I do the derivative of y first with respect to u, and then I multiply that result by the derivative of u with respect to x. And remember our little memory device, if you think of canceling these du's on the right side, you'd end up with dy over dx, which matches the left-hand side. And we know that we've got these factors on the right written out correctly. Okay, well, that means I need each of these factors. The first factor I need is dy du. So I go up to here where I've expressed y as a function of u, and I simply find its derivative. So if y is equal to cosine of u, then dy du is just the derivative of cosine u with respect to u. That would just be minus sine u. So this first factor on the right-hand side of the chain rule becomes minus sine u. All right, the other factor that I see is du dx. And right here I have u expressed as a function of x. So if I want its derivative, the derivative of u with respect to x, all I have to do is take the derivative of the right-hand side. Derivative of 4x squared minus 5, I can do that. That's equal to 8x. So that's the second term that goes down here in my alternate form of the chain rule. Du dx is equal to 8x. And that's what dy dx is equal to. So I've got dy dx is equal to minus sine u times 8x. Well, that's kind of a funny answer because it has a mixture of u's and x's over here on the right-hand side. So I don't really like that. I would like to rewrite purely in terms of x. So I want to rewrite this purely in terms of x. So can I do that? Well, the 8x is fine. That's already written in terms of x. The thing I don't like is this u. But what is u in terms of x? I can either go over to here where I've written it. U is the same thing as 4x squared minus 5, or you can go back up here where you made your original designation for u. We said u was 4x squared minus 5 up there as well. So we know what u is in terms of x, and I'm just going to plug that in down here in place of my u. So dy dx would be equal to minus sine of u, but u we said is 4x squared minus 5. and then I have a times 8x, and that factor was already in terms of x, so that one was okay. The only thing I would do at the end here is probably to put this shorter factor in front. So 8x times a negative would give me a negative 8x sine of 4x squared minus 5. And that's how I'd write my final answer. Now you might notice that if you use the chain rule in the traditional way that we're used to, by taking the derivative of the outer, we get minus sign, evaluated at the inner is 4x squared minus 5, and then times the derivative of the inner, take the derivative of what's inside, I get an 8x. Right here you can see that we could get to this line of all of this derivation very easily by using the chain rule in our original form. So I think the chain rule in the original form is a little bit faster, but some people like to think about it this way, and that's perfectly fine. And when you get used to using it in the alternate form, it does go fairly quickly. Now, there is a remark down here at the bottom. I'm not going to talk about that. It's really talking about the case of the chain rule where we have a composition of 3 functions rather than just 2 functions. And I was going to make a remark about that using the alternate form of the chain rule. I'm crossing this out because we've really already talked about this. We did it with the original version of the chain rule where we had some examples composing 3 functions, a function inside another function, and you might remember that we got a sort of a chain of factors because we worked from the inside out, we applied the chain rule twice, and so we got a chain of 3 factors, and that's where the name chain rule really comes from. But since we've already talked about it for the other form of the chain rule, I'm not going to go through that again here. And so that does it for our section